All right, we started section 3.4 last time, and the last thing we had done was actually taken a look at properties of whole numbers, and we had done this example. So we had a lot of properties for multiplication. The same ones we had for addition. We had commutative and associative and closure, and we had a multiplicative identity. And then we have this additional property of the distributive property that allows us to combine addition or subtraction with multiplication. And we also had one that was the zero multiplication property, and it said that if we multiply by zero, we get zero. So this example 3 is an example like a section C kind of question. JJ claims that the following is true by the distributive law, where A and B are whole numbers. 3 times A times B is 3 times A times 3 times B. How would you help him out? So the first thing you have to do, kind of like the question we just looked at with the student work just a minute ago, is to decide, is JJ right or wrong? Does this actually work? So think about that for a second. Is 3 times A times B equal to 3A times 3B, or 3 times A times 3 times B? So what do you think? It looks like the distributive property. Do you notice how it looks different than the distributive property? What's that, Ty? There's no addition. And there's no subtraction for that matter either, right? There's no addition or subtraction. What operations do you see present? Just multiplication. That's right. I only see multiplication. Do you only see multiplication looking at it now? Okay. So it doesn't actually match the distributive property that he's claiming to use. Now that doesn't necessarily mean it won't work, but it means we need to be a little bit more careful about associating it with that word distributive because it's not really that same property. So one way that we could check to see if it's true is we could put some numbers in for A and B. True? So let's actually give that a try. What would you like to let A and B be? 2 and 3. It's probably important as a general statement not to let them be zeros and ones because a lot of things fall apart with zeros and ones that don't work in general. So if we did 3 times 2, that's the left side, and the question mark is does it equal 3 times 3 and 3 times 2? Okay, so what is 3 times 2? 6. And what is 6 times 3? 18. It's okay. You're good. You're good. It's okay. How about 3 times 3? That's 9. That's the 9. You were just ahead of me. So you guys just want to be ahead of me today. It's okay. How about the 3 times 2? Found 6. And what's 9 times 6? Okay, at the very least, you should be able to tell me it's not 18, right? It is 54. It is not 18. These are not equal. So we have an example here that shows that it doesn't work. What did we call that kind of an example?
Counterexample.
That's counterexample. Very good. So this is a counterexample. It shows that this is not a true statement. So developing our intuition about whether or not a student's work is right or wrong, it's really good to check whether they're right or wrong before we start deciding anything in general. The student is not correct. Okay, the student is not correct. We've got a counterexample. And showing the student the counterexample could be very helpful. It might be a little confusing that we chose a 3 since there's a 3 in the original problem. So you might choose not to use a 3 just for that reason. But it definitely shows it's wrong either way. Okay, so we probably need to help JJ to know that first. So JJ is not correct. And you can say a counterexample is if A is equal to 2 and B is equal to 3, then 18 does not equal 54, right? We worked through it. We showed that this is a counterexample. So it's not actually going to work. Any idea why that's happening? It's not the distributive property. We already said that because there's no addition or subtraction. Can you tell what property you could use here to rewrite it? Look back at your property list. There is a property that allows us to rewrite this or something, to think of it differently anyway. Yeah. 3 times A times B could use the associative property. So it equals 3 times A and then times B. You could even flip the A and the 3 around, or group the 3 with the B and use some commutative properties, right? Or B times 3A with the commutative property. But it's not a, let me write it down, we've said it out loud, but it is not distributive and the reality is because there is only one operation. So only one operation. Multiplication. Okay, is that all right? So be careful about things that sort of appear in the same way as another property and make sure that they really do match that property identically. All right, we're going to take a look at some stuff with exponents. Exponents is repeated multiplication, and we're in the multiplication section. So if we have a to the n, this means a times a times a times a, right? All these, n times. So for a rational number a is called the base, and n is called the exponent. I'm going to show you the first 4 here. I'm just going to tell you the properties, and then I'm going to show you why they work. So when you have a to the m times a to the n, this is a to the m plus n. We add exponents together, and I'll show you an example in a sec why. So if I add exponents when it's multiplication, I will subtract exponents when it's division. Sort of seems like a natural analog to that. If I have number 3, a power raised to a power, that's when I multiply the exponents. Notice the difference between 1 and 3. What do you notice that is different when you look at the expression that's typed on 1 versus 3? That's in what I wrote. I mean in what was typed first. There's parentheses. That's a definite one that you should notice. There's parentheses. There's also one more thing.
The n doesn't go to the a by itself.
Okay, so let me rephrase what you said in a slightly different way. There aren't 2 a's. Do you see that? So when I look at 1, a is written twice, but when I look at 3, a is only written once. And then, as noted as well, there's parentheses involved. So those are important things to be aware of. They look similar, but they are not the same. And the fourth one, has parentheses again, but it has 2 pieces inside, right? And there is a property here that feels like our distributive property. It's a to the m times b to the m. So we do have this sort of distribution of the power going across and showing itself like this. Okay, I want to explain to you why each of those properties works the way that they work. Because at some point, somebody's going to have some kid that's going to say, but Mr. Haynes, why? Right? And you may not know when they say this to you why, but you should be able to say, you know what? Let me find that information for you because it's been a while since I've thought about it, and I'll talk to you about it next class period. And it's not hard to go find that information, especially if you've seen it before, right? So let me take a look with you as to the why on these. So the first one is supposed to be a to the m plus n. And I'm going to show this as an example. This is not a proof because I'm doing very specific numbers, but it's a pretty good justification in our minds as to why it works. Let's say we have a cubed times a squared. So what does a cubed mean? Well, by the definition, it means a times a times a. Does everybody agree? What does a squared mean? Well, a times a. And how many a's do you see here? Sorry, did somebody say it? 5. I didn't hear. My earring. I'm at a distance with the way that this is echoing up here, so I'm not hearing very well at the moment. So a to the 5th. And if you take a look at this, how do you get then from 3 and 2 to 5? You add them, right? So if you were in an environment where you forgot which one was what, if you do a real quick example, you can probably convince yourself pretty quickly about which one you should be doing. Do I add or do I multiply? All right, the next one is a to the m over a to the n, and this says that we're supposed to subtract. And again, let me give you a justification by example. We're going to do a to the 4th over a to the 1. So a to the 4th is a times a times a times a, and a to the 1 is just a. Now, one of the properties of rational numbers, which is something we do later we do it in Prop and Stat, but is that when you have multiplication, all multiplication, this doesn't work if it's addition on top, it only works if it's multiplication on top, then we can actually cancel one of these out because we can divide the numerator and the denominator both by a. That leaves me with 3 a's on top, otherwise known as a cubed. How do I get from 4 and 1 to 3? Subtract, right? Yeah. 3 is supposed to be multiplying a to the mn. So again, we'll use an example. Mm-hmm. Okay. Do you have it?
Yeah, sorry.
It's okay. I want to make sure everybody else has it too. We're good? Okay. Let's do the same 3 and the 2 we had before. A cubed squared. Well, we know what a cubed means. It means a times a times a. You can put the dots between them or not. For space sake, I'm not going to right now, but this is squared. Squared means we multiply something by itself. So this 3 a's are multiplied by themselves. And if you count them up, how many a's did that give you? 6. And how do we get from 3 and 2 to 6? We multiply them. Yeah, we multiply them. And the last one is a to the m, b to the m. So ab cubed, so cubed means multiplying something by itself 3 times. So this is actually ab times ab times ab. Okay, that's what it means for it to be cubed in its truest sense. But do you see this looks a lot like JJ's problem where he has multiplication in parentheses? And we have properties that allows us to manipulate that. We have properties that allow us to regroup things, that's the associative property, and we have properties that allow us to switch the order of things, that's the commutative property. And if we regroup and reassociate enough times, we will be able, if we do it very carefully anyway, to get all the A's together and put all the B's together using commutative and associative properties. And what is A times A times A? Well, it's A cubed, and B times B times B is B cubed. And then it looks like the property on the left. Now, as you do these problems, I'm not asking you to write them out like this every time. That's not the point of what I just did at all, okay? The point is to help you understand where those properties come from. And now that we've done that, we're just going to use the properties. So when I see a problem like number 4A here, I notice, hey, look, there's a base 5 and they all match, right? And they all have these exponents together. And I look for the 4 properties and I ask myself which one of the 4 properties seems to apply to this particular problem. And which one seems to apply? 1, 2, 3, or 4? 1. It looks like 1. There's 3 of them, but besides the fact that there's 3 of them, it looks like problem 1 with just an extra value on the end. And it works the same way. So we take that 5 and we add the exponents together. So 5 to the power 10 plus 2 plus 4, and 10 plus 2 plus 4 is 16. Now B is a little bit different. What makes B look different than A?
They don't have the same base.
They do not have the same base. Does everybody see that? A 6, a 2, and a 3. So you can't just merge them together and call it like, well, it's kind of like the first one. No, it isn't. The bases have to match for that to work. So there's two different ways we can do this. Let me show you both of them. This one right here, the second, we could notice they both have a power of 3. Do you guys see that? And so we could kind of undistribute that power on the outside and put the 2 times 3 inside. What we're doing is we're using property 4, but we're just using it backwards of the way we established it. But equalities work forward and backwards, so that's okay. And it's actually pretty nice because what is 2 times 3? 6. And now I have 6 to the 4th and 6 to the 3rd, which would give me 6 to the 7th. Okay? There's another way to do it. Okay, this is a perfectly valid way to do it. This is a perfectly good answer. There's nothing wrong with this. But there is another way to think about this. Instead of thinking about merging the 2 and the 3 together, we could take the 6 and say, well, 6 factors. How does 6 factor?
2 times 3.
It's 2 times 3. So instead of merging something together, I could separate the first 6 apart. And then I could use property number 4 where I distribute that power 4. So this is 2 to the 4th times 3 to the 4th plus 2 to the 3rd times 3 to the 4th. Hang on. That's a 4 at the end, 3 at the end, isn't it? My apologies. This is supposed to say 3 cubed. And then I would find the ones that match. So, right, this is a base 2 and this is a base 2. And I would combine their exponents. So what is 4 plus 3? 7. And then I would take the other 2 pieces and notice that their bases match. They're a 3. And their exponents happen to also be 4 plus 3. They wouldn't have to be, but they do. And I would get a 7 there. And this is a perfectly reasonable way to leave it as well. Obviously, there's a relationship between the 2 that I've underlined. One is the merged version and the other one is the factored version. But for the purposes of what we're doing, there's neither one that's better than the other. They're better in their own unique ways. 6 to the 7th is better because it's sort of consolidated. The 2 to the 7th and 3 to the 7th is better in the sense that it's in prime factors. Okay, so either one's perfectly reasonable for what we're doing. All right, next up, multiplication algorithms. So we're going to take a look at a number of multiplication algorithms. The first one is called expanded standard algorithm. We have the expression 48 times 32. And what we're going to do is we're going to expand it. We've done an expanded form in both of our previous lessons about these operations where we separate them on place value. So 48 is 40 plus 8. 32 is 30 plus 2. Shake your head if you remember separating them like this. Okay, good. Now, we are going to multiply them now, not add or subtract. And the way that we multiply is we multiply them piece by piece. So I'll take my 2 times my 8 and my 2 times my 40. So 2 times 8 plus 2 times 40. And then I'll take my 30 times 8 and my 30 times 40. And you can go in any order, doesn't matter. Plus I have 30 times 8 and 30 times 40. So once again, like we noticed when we had that question C question in the last homework that you just turned in, this becomes single digit multiplication with some trailing zeros. We've got some extra zeros going on there, but otherwise we're really multiplying with single digits, right? So if I look at 2 times 8, that one really is single digit times single digit. But when I look at 2 times 40, well, it's really 2 times 4. What's 2 times 4? 8. And how many zeros? 1. And then if I have 30 times 8, well, that's really just 3 times 8. 3 times 8 is 24. And I have 1 0. And then I have 30 times 40. Well, what's 3 times 4?
7.
That's addition.
I'm sorry.
12. Yep. So we have 12. And then how many zeros on this one, though?
2.
There's actually 2 zeros on this one. So we end up with 16 plus 80 plus 240 plus 1200. We would add that up in the same ways that we've added them up before. I'm not going to go back to belabor that point, but if we add them, we get 1536. And you should be able to make sure that this is right because you have a calculator, right? Make sure that you didn't make a mistake in doing it for sure. But this is the expanded algorithm. We're multiplying all the pieces together. A visual for the expanded algorithm is called the partial products algorithm. This one is actually my favorite one of these. And so we take again the 48 and we write it as 40 and 8 like this. And we write a box underneath it. Our box is a 2x2 box because these are 2-digit numbers. If I were doing 3-digit numbers, I'd have a 3x3 box. Or if I did a 2-digit by a 3-digit, I have a 2x3 box. Okay, the box is going to be represented by the number of numbers I've got. And you can put the 30 and the 2 either on the right or on the left. I'm choosing to put it on the right because in a minute we're going to have another one that's going to force us to put it on the right. So if we just always put it on the right, we don't have to remember which one is the one that I can move around. We'll just always put it on the right and it doesn't matter. Each of the boxes then is a row and column that multiplies. So when I look at this box, it's in column 40 and it's in row 30. Do you see that? Column 40, row 30. So that's the product that I write in that box. So 40 times 30 would be the same 1200 I got before. It's still doing all the same multiplication pieces I did just a minute ago. It's just doing it in a visual box format instead. So I have a 240, I have an 80, and I have a 16. And the sum, when I add it all back together, is still 1536. Now, here's why I like this method. I mean, I like the box because I'm a visual person. I like the visual stuff. But the real reason I like the method is because you can justify where these things are coming from. Because what happens when I do the number 48 is what it really means is that the length on the side is 40 long and 8 long. Can you imagine measuring it out like for real? And if I did 32, I'd have to separate it and it would look kind of like this down here at the bottom. This length would be 30 and this would be 2. You could put it on a grid. Like I could get graph paper if the numbers are small enough, right? And I could actually have the kid count and see that the boxes do what we're telling them that they do. You can see that this 1200 is much bigger than this 16, right? And so forth with our 240 and our, what was it? 80. So the box's dimensions actually give me the individual areas. So it harkens back to that area construct that we did when we were modeling last time, right? There's an area model. This is the picture that really goes with it the best. So I really like this one. My daughter, Abby, who's about y'all's age, she's a junior in college. When she first learned to multiply, the standard algorithm, which we haven't gotten to yet, just wasn't working. And she was really pretty good at math. I mean, like she's got a math minor now, but even then she was pretty good at math. So it was really bothersome to her that she wasn't getting it. And so I showed her this one. This is my favorite. She didn't like this one either. That was so sad. But the one that she did likes the next one. So the lattice method is how she learned to multiply. And eventually, obviously she doesn't use the lattice method now, right? But this was the one that helped bridge that gap until she could figure out what was going on with and understand the standard algorithm better because it's faster. So here's the way this one works. Instead of writing it as 48, we write a 4 and an 8. And instead of writing it as 32, we write a 3 and a 2. We put the box, and the box divides into 4 pieces, again, because it's a 2-digit by 2-digit number. All good so far. The setup looks very similar to the last setup. But like our lattice method for addition, we split the boxes like this. Okay? Each of the boxes is the multiplication of the row and the column. Again, just like we did with the partial products one just a minute ago. So the first top left-hand box, and you can start wherever you'd like, is 4 times 3. It's the number 12. So the tens digit goes in the top corner and the ones digit goes in the bottom corner. We're just going to go across the top. I have 8 times 3 is 24, so the 2 goes in the top and the 4 goes in the bottom. 4 times 2 is 8, so it's a single digit, goes down here. And then 8 times 2 is 16, so I have 1 and 6. Okay, so that's all the multiplication. And then we multiply, or we draw out, all the diagonals. And we do have to start in the bottom right-hand corner. So as I'm about to do what I'm about to do, all of these pieces on the outside are not involved in what I'm doing. We are done with them. They were involved in the multiplication. They are not involved in the next step. So in the bottom right-hand corner, I have a 6, so the 6 comes down. And then I go down the next diagonal like this. I add 4 and 1 and 8 together. What does that give me? 13. So I write down the 3 and I carry my 1. And then I do the next column. 1 and 2 and 2 is 5. And then I have my 1 on the top left-hand corner. So what all 3 methods of these do, if you didn't pick up on it, is they separate the multiplication step from the addition step. I'm not multiplying and adding within the same space. I'm doing all my multiplication first and then I'm doing all my addition second. So let me show you that in contrast to our standard algorithm. The one, I don't even think I have a blank for it. I don't, but I'm going to write it in. Let me show you with the standard algorithm what happens and why that can be confusing for our kids. So if we do 48 times 32, we start with the right-hand column. That's fine. So you did 2 times 8 and you get 16. But you can't write a 16 down. You have to write a 6 down and you have to carry the 1. Again, that's not so much different than what they did with addition. And then we multiply on the diagonal. We have 2 times 8. I didn't say that right. 2 times 4, which is 8. That's what I wanted. 2 times 4, which is 8. And then for some reason, in the middle of multiplying, I add the number 1 to it. Can you see why that feels a little bit awkward? In the middle of multiplying, I add the 8 to the 1, and I get a 9. And then, mysteriously, I just put a 0 in this spot. There's a reason, but it looks kind of like magic. It just showed up, right? I put the 0 in the spot, and I go on, and I say, okay, well, 3 times 8, now that's 24. There's a 4, and I carry the 2, and if I'm not careful, I need to make sure that 1 disappears, or it's going to get in the way, because now it's a 2. And I do 3 times 4 is 12, and again, in the middle of my addition, my multiplication, I add the 2, and so I get a 14. And then if that weren't enough, I get to add again. And I end up with 1536 from what I had done before. This is messy. It is complicated. And the reason, but it's very efficient. It's the quickest one. Right? No doubt. It's very quick. It's consolidated space for the most part. We don't always write it thoroughly big out like this. So it's very efficient and it's very space friendly, but it does merge a lot of operations together for a child that's still trying to figure out all these operations or separately. Does that make sense? Okay, so we will stop for today.